In this video, we're continuing a problem about distribution of traits with polygenic inheritance. We are looking at height, which is a trait controlled by hundreds of genes, but we're simplifying it down and pretending that it's only 4 genes. We care about, for these offspring, we care about how many contributing factors they get. Contributing factors are shown as capital letters, and those are going to be signals to produce some element that we're interested in. In this case, there'll be signals that increase the height of the individual. So, in our last video, we looked at the genotype of mom and dad. We figured out what gametes were possible from those individuals, and then we made a Punnett square to see what the genotypes of their offspring could be. Now, rather than look at individual genotypes, we're just going to look at how many contributing factors each one of these has. To do that, we could go through and count the number of capital letters in each one of these. I think it's going to be a little faster, though, just to re-represent this with the number of contributing factors instead of with the individual genotypes. So let's set up another table then. We'll make it identical in size to the one up above. So we'll have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 rows and 4 columns. Except this time, instead of writing in each genotype, I'm just going to write down a number, and that number represents how many capital letters there were in the above table. So I'll start with the gametes that mom and dad were producing. So top left here, we've got big A, big B, little c, big D. That is 3 contributing factors. Here we've got 2 contributing factors. Here we've got 2 contributing factors. And here we've just got the 1 contributing factor. So dad has 4 gametes that he can produce with each of those numbers representing the contributing factors in each. Let's do the same thing for mom. She's got 4 on this one, 3 here, another 3 there. Right there is 2, the big A and big B. That's a 3. We've got another 2 here. This one's another 2. And lastly, we'll have just a single contributing factor. So then in the middle, our crosses are going to have the contributing factors from mom and from dad. Our offspring will have the contributing factors from mom and from dad. So in this spot, I'll just add up the numbers from dad up top and mom on the left. So that'd be 7 for that offspring. And then 6 here, 2 from dad, 4 from mom, 6, and 5. So I'll go ahead and complete that table. Alright, and there we go. We've got a new table that shows how many contributing factors each one of these offspring would have. We see at the low end we've got 2 contributing factors, and at the high end we've got 7. Now if we think about what's possible for a 4-gene trait, there's 8 letters there. At most, they could all be capital letters. They could all be contributing factors. So the most we could have would be 8 contributing factors. The least we could have would be 0 if they were all lowercase letters, no contributing factors. We don't see the very high end of the range or the very low end of the range possible from these parents. Now let's try and condense this data even a little bit further to understand how these potential offspring are distributed. So we're going to make one more table. This one with 2 columns, one for the number of contributing factors, and one that we'll call the frequency, which is how often we expect that to happen. So for example, if we looked at 2 contributing factors, there's only one case out of the 32 here where we would expect that to happen. So I know that we have data stretching from 2 all the way up through 7. Talking and writing at the same time, I'm not doing very well. There we go. And so let's start recording these. 2 only shows up once out of the 32 times. 3, I've got, let's see, 1, 2, 3, 4, 5 times out of 32. 4, we've got a few more times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 32 times. 5, got quite a few of. 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 32. 6, we're starting to taper off again. Got 1, 2, 3, 4 of those 6. Oops, I missed one. 1, 2, 3, 4, 5 of those. And then 7, I only see once out of 32 again. And I'm just going to do a quick check here. 1, 6, plus 5 is 6, plus 10 is 16, plus 9 is 25, plus 5 is 30, plus 1 is 31. Okay, so it looks like I missed one. Best just go back and check all of them. Actually, maybe we can scratch that. I notice here we've got 1 and 1, 5 and 5, 10, but only 9 here. Let's double check the 5s first. We'll see if that pattern holds out. So let's see, 5s, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, it was 10 instead of 9 there. Okay, so it looks like 4s and 5s are the most common, kind of a mid-range there. And if we look back at what Mom and Dad had, see, Dad had 1, 2, 3, 4 contributing factors. Mom had 1, 2, 3, 4, 5 contributing factors. So our two most common outcomes would be Mom's height or Dad's height. That makes some sense. But notice that we still have a lot of other possibilities. We're going to do one last step here, and that's to make a histogram, that is a bar graph, to show the frequency of these, so we get a visual of this. So let's set up a little graph here. And on this side I'm going to put frequency, and that'll be 30 seconds. All of these are out of 30 seconds. And down here we'll put number of contributing factors. And then, let's see, we got 0, 1, 2, 3, 4, 5, 6, 7, 8. Those all labeled. Oops. And then for frequency, at most we had 10. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Perfect. Okay, and then we'll plot each one of these. We have no possible outcomes with 0 or 1 contributing factor, but we do have one at 2. Shaded in a little bar graph here. Let's see, 3 contributing factors. We need to go all the way up to 5. And 4 contributing factors all the way up to 10. And another one like that for 5 contributing factors. 6 contributing factors. We need to go up to 5 again. And at 7, we're up to 1. Alright, now we simplified this down just to 4 genes. So this is not quite the same picture we'd expect to see with actual possibilities for height. But what we notice is something that's pretty characteristic of these. I'm just going to draw in a bit of a shape like this. There we go. That curve that has a high point in the middle where the most frequent traits are, and then it drops off on the 2 sides, that's called a bell curve. And so something like height matches a bell curve pretty well. We have lots of people who are at sort of the middle ground for height. We have not as many people who are significantly shorter or taller than that, and then very few individuals who would say are extremely short or extremely tall. So our frequency drops off on the ends on this. We still have the possibility for a wide amount of variation, but what we see is that most individuals are sort of in the middle range, and fewer individuals are on the outer parts of that range. This will set up, though, the idea that a range of possible outcomes occurs, and that occasionally being on one side or the other of that bell curve is going to give you a big advantage, and as a result may tend to shift that entire curve over. Notice that our curve has its high point at 4 or 5, and that's also where our parents were. Now, if we imagine trying this again, where our parents have 6 or 7 of those contributing factors each, it makes sense to think that this whole curve would shift over to the right. Not that we couldn't still get fairly short individuals from those pairings, but we'd expect that most of the offspring would be taller, or the offspring would be more likely to be tall on these ones. So that'll do it for this one. We are going to continue learning about variation, and next up is mutations.